Part 3. The Non-Linear Laws. Interdisciplinary Science. Introduction to Part 3. In Part 3, we turn to nonlinear systems and to the interdisciplinary science that addresses them, to chaos, complexity, and systems thinking generally. According to nonlinear science, the world does not behave in a linear fashion, with Newtonian regularity, with cause and effect discrete and identifiable. The mathematician Stanislaw Ulam commented that calling the study of chaos nonlinear science is like calling zoology the study of non-elephant animals. Ulam has a point, because the modern world is full of non-linearity, but he was exaggerating. It should be stressed that some things are linear, and here Newtonian physics still work. But many of the important and interesting things in life are non-linear systems. The whole is more than the parts and comprises something qualitatively different from the parts. Linear analysis can't help when studying complex systems, but the relatively new interdisciplinary sciences of chaos and complexity can. We review these in Chapter 9. In Chapter 10, we find out how to achieve more with less, with the tool of the 80-20 principle. We also derive insight into nonlinear systems from the power of weak ties, von Foister's theorem from cybernetics, control theory, and Fermat's principle of least time. Chapter 11 covers the nonlinear aspects of growth, technological change, networks, and the new economy. It revisits punctuated equilibrium and introduces the related and extremely useful concept of the tipping point, which helps us predict whether and when a new trend or product is going to take off. It shows the key role of technology in driving growth. The chapter also introduces the law of increasing returns, which overturns most of traditional microeconomics and shows how the construction of temporary monopolies may be both inevitable and in the public interest. Chapter 12 looks at how systems theory can help us sustain success, despite the traps of the paradox of enrichment, the law of entropy, and the law of unintended consequences. Chapter 9. On Chaos and Complexity. Chaos is when any system is so complex and irregular that it appears to be random unless you know a lot of hidden information about it. Chaos is lovely. It is absolutely wonderful. It is full of all sorts of intriguing forms and behaviors. Ian Stewart. The third great scientific breakthrough. Chaos and complexity are probably the most important scientific innovations of the late 20th century. They are interdisciplinary concepts and fields of study, drawing on mathematics, biology, physics, economics, and many other disciplines. Although it is too early to be sure of their place in the history of science, many believe that they rank alongside or just behind relativity and quantum theory, comprising the third great scientific breakthrough of the last century. Chaos and complexity also throw up insights that are very congruent with, but also complementary to, those already provided by relativity and quantum theory. As one physicist comments, relativity eliminated the Newtonian illusion of absolute time and space. Quantum theory eliminated the Newtonian dream of a controllable measurement process, and chaos eliminates the Laplacian fantasy of deterministic predictability. Chaos. As suits its Alice in Wonderland nature, whenever I use a word, it means what I want it to mean. Chaos, in this context, means the concept or field of study of chaos. Very few scientists working on chaos call it chaos theory. And chaos is not necessarily, or even usually, chaotic in the ordinary sense of the word. Let's face it, chaos is a bad name, because the processes studied often reveal beautiful and intricate patterns. The processes are only superficially chaotic. Underneath, there is a deep, if irregular, order. Chaos is the search to identify and understand nonlinear patterns that have been ignored by traditional science. The fun of chaos is that if you look at structures in nonlinear systems, they are very similar, regardless of the phenomenon. It could be the weather, the economy, the way cities are organized, a set of numbers, snowflakes, coastlines, stars in the sky, or a series of stock exchange prices. Chaos has its roots in quantum theory and in mathematical work, during the 19th and early 20th centuries on chance and probability. Quantum theory tells us that very small things like atoms and photons do not behave in a linear or predictable way. They really are chaotic. The brilliant French mathematician Henri Poincaré wrote with great insight in 1908, "A very small cause, which escapes us, determines a considerable effect which we cannot ignore, and then we say that this effect is due to chance." Sensitive dependence on initial conditions. Poincaré is really the intellectual forerunner of chaos, where the central insight is sensitive dependence on initial conditions. Many physical systems exhibit sensitive dependence on arbitrary initial conditions and are therefore essentially unpredictable. The classic example is the weather. It used to be thought that with enough data and computing power, it would be possible to predict the weather reliably, months in advance. We now know that this is impossible because weather is subject to extremely sensitive dependence on initial conditions. The butterfly effect. In 1972, Edward Lorenz, a meteorologist at the Massachusetts Institute of Technology, gave a paper provocatively entitled, "Predictability: Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" The question, he said, was unanswerable but illustrates the nature of the weather. For many years, Lorenz had used computers to model the weather, hoping to improve long-term forecasts. His pioneering work showed that eddies and cyclones obeyed certain mathematical rules, yet never repeated themselves. Long-term weather forecasting, he concluded, was impossible, for extremely interesting reasons. Although he could model the influences on weather, minute changes in a couple of variables, extrapolated over a month or beyond, could produce totally different results. Lorenz's insight was not just that small effects have huge consequences. This is an old story, embodied, for example, in the Prussian verses about the kingdom being lost for want of a horseshoe nail. His real breakthrough was to demonstrate that the future of weather was literally uncertain, even if we knew everything there was to know about all the influences on it. The weather makes itself up as it goes along, as does evolution, and as do vibrant economies. The search was on to understand complex, nonlinear systems. Most interesting things in the universe are complex systems and chaotic. Both chaos and complexity, like quantum physics, are based around the realization that many things in the world are not linear, not easily predicted, and not simply the sum of their parts. Complex systems, like the weather, cities, Economies, galaxies, insect colonies, packs of wolves, brains, and the internet are not stable and spend little or no time in equilibrium. Yet they can all be described and often analyzed by using the concept of chaos, and, as we shall see later in this chapter, the related concept of complexity. Many of these systems return repeatedly to a position close to where they were before. Complex systems may have simple causes. Much of their behavior may be described by simple equations. For example, the way that leaves are blown by the wind. And chaos has shown that simple rules of behavior can lead to amazingly complex results, but again, ones that can be understood in terms of a set of simple subsystems. Certain characteristic patterns recur, yet with infinite, unpredictable variety. Insights from chaos into the physical world. One milestone in the emergence and naming of chaos was the work of mathematician James York around 1970. York and other mathematicians pointed out that when confronted with nonlinear systems, the typical response of mathematicians was to attempt to solve them by substituting linear approximations. York demonstrated that this was unnecessary. Even nonlinear systems that were very sensitive to initial conditions could actually be modeled. Computers could take, for example, biological data relating to fish populations and produce a graph. Regularities could then be detected that were totally counterintuitive. What's the connection between cotton prices and the Nile? At about the same time, Benoit Mandelbrot, also a mathematician, was working in IBM's Pure Research Department and using its most powerful new computers to analyze cotton price data. He showed that there were patterns for daily and monthly price changes that matched perfectly. The degree of variation had remained constant over 60 years. There was unexpected order within the disorder. Mandelbrot found the same patterns in all the data he analyzed, including variations in the level of the River Nile over several millennia. The more research that was done in meteorology, in biology, in geology, in physics, in chemistry, in economics, and in many other areas, the more it became apparent that there were unsuspected regularities that could be described by the relationship of large scales to small scales. Mitchell Feigenbaum, a physicist at the Los Alamos National Laboratory in New Mexico, soon after conducted a series of calculations to measure the size difference between geometrically converging sets of data, such as Mandelbrot's cotton prices. His calculator repeatedly came up with the same number, 4.669. Feigenbaum had stumbled across one of the most startling properties of chaotic systems: universality. Universality means that on some dimensions, different systems will behave identically. At a conference at Los Alamos in 1976, one of Feigenbaum's colleagues commented, "It was a very happy and shocking discovery that there were structures in nonlinear systems that are always the same if you look at them the right way." How long is the coastline of Britain? Mandelbrot showed that there is no right answer to this question. It actually depends on your measuring instrument. With a small enough ruler, measuring every tiny indentation, the distance approaches infinity. Fractal similarities. Mandelbrot coined the very useful word fractal to describe things that are very similar to each other, yet not identical. Things like coastlines, clouds, cotton prices, earthquakes, or trees. Patterns are endlessly repeated, yet also with endless and unpredictable variety. Plotting data from nonlinear systems reveals strikingly similar patterns regardless of the actual data being plotted. For example, the year-to-year graph of cotton prices looks eerily like the shape of the month-to-month cotton price variations, even if the scales are different. Business is fractal. No situation is quite like another, but there is a limited set of key factors that always resemble each other. Business outcomes are utterly unpredictable, which is why the quest for a deterministic science of management, if you do X and Y, then Z will result, is futile and naive. Yet there are recurrent patterns that are worth studying and recognizing. The fact that business is fractal is the best justification for the case study method used in business schools, although this would be much more useful if we could map the different fractal patterns for different types of businesses, something no one has yet done. Research into fluid turbulence by David Ruel in mathematical physics in the early 1970s led to the idea of a strange attractor, a fractal object that is a point and can be modeled mathematically to explain turbulence. Strange attractors could also depict the chaotic behavior of a rotor with extreme mathematical precision. The theory has since been used in astronomy to explain how stars form islands and chains of islands in the sky, and in fact to map the trajectory of any dynamic system that is sensitive to initial conditions. Although not strictly linked to chaos, let's digress briefly to look at two laws of chance, one from statistics and probability theory, and one from the study of chance in history. Principle of impotence. This theory says that it's impossible to devise a successful gambling system to be used against a fair coin or other genuinely random device. Where there is chance involved, it may be impossible for managers to do better than flip a coin. More generally, at what point do you make an important decision? When are you 70% sure that it's right? 80%? 95%? Whatever percentage you choose, remember that your estimate may be way off and will usually be too optimistic. Remember also that analysis and delay have costs. Fear not. The principle of impotence provides a good excuse for action based on insufficient data. Of course, you shouldn't decide cavalierly, but equally don't allow a difficult decision where there will always be great uncertainty to paralyze your progress. The hinge factor in history. Historians have long known that chance events can turn the course of history. The crucial event, the hinge, may be something small, banal, and unexpected. A recent book gives many interesting examples of the hinge factor in history. Here are three. In the American Civil War, the Confederate States might have won easily and early had General A.P. Hill not lost the plan of attack drawn up by his superior, General Robert E. Lee. Hill used Lee's handwritten plan to wrap a couple of cigars. These were mislaid and found shortly afterwards in the abandoned Confederate camp by a sergeant from the opposing Union Army, who passed it on to his supreme commander, General McClellan. The Battle of Antietam was a surprise Union victory as a result. A similarly trivial blunder sealed the fate of Germany's Bismarck, the world's fastest and most powerful battleship. Other things being equal, the Bismarck should have been able to block supplies from America to Britain during the Second World War. But in 1941, Admiral Gunther Lutyens neglected to fill her up with fuel in his haste to leave Norway and sink the British battleship Hood. Although the latter went down with 1,500 fatalities, the battle caused slight damage to two of the Bismarck's fuel tanks, and this together with the failure to fill up in Norway, meant that the ship had to travel much slower than normal as it made for occupied France. British warships were therefore able to catch and sink her. Why did communism collapse in 1989? Apart from the vanity of Gorbachev, who played footsie with the West when he could equally well have maintained repression, a very important catalyst was an unscripted chance reply during a TV interview with Günter Schabowski, who'd just been appointed Communist Party spokesman in the German Democratic Republic, the old East Germany. When, the interviewer asked, would East Germans be allowed to travel freely to the West? Schabowski shot back petulantly, "They can go whenever they want. Nobody will stop them." The audience was stunned. Then there was bedlam. Thousands of East Germans poured over the border, and communism was dead. Chaos and complexity and history tell us that business is uncertain and risky. Past success gives no exemption. Ergo, take risks. Outcomes are uncertain anyway. Evolutionary psychology says that when we are comfortable, we take the fewest risks, despite the fact that we could afford to. Because too few people take risks, the rewards from doing so are, in aggregate, more than they should be. In business, this does not apply to gambling, where the odds are precisely correct when there is no house, and miserable when someone else is making a living out of it. Successful businesses take too few risks. As long as you avoid bet the company moves, take as many risks as you intelligently can. Chaos, chance, and business. The concept of chaos is that although the world largely comprises non-linear systems, there are patterns discernible within the irregularities. Disorder in the universe is constrained. Chaos and chance do not lead themselves to tracing simple causal links, which is what turns on most of us in business. Yet there are some very useful morals for business. Here are 8. 1. There is always some pattern or order in apparently random or disordered data. Patterns exist. The only question is whether we can detect them. All markets generate patterns of behavior and response. 2. Analysis may not be the best way of finding the hidden order. Analysis may be incapable of finding the answer if the system is reasonably complex and interdependent. The human brain has the flexibility and imagination to discover the pattern. Therefore, if you want to understand a market, it may be better to immerse yourself in it and wait for the inspiration to come than to search for data and analyze it. 3. Simple systems do complicated things. There may be 3 or 4 key things that, combined with chance, better called sensitive dependence or initial conditions, lead to incredibly complicated behavior. Try to isolate the key variables, the main causes that interact with each other. However, resist the temptation to reduce everything to one main cause or effect. 4. Complex systems can give rise to simple behavior. Behavior is a better and easier guide to a complex system than complex structural analysis. When looking at complex systems, such as markets, customers, or competitors, look for characteristic patterns of simple behavior. For example, if a competitor always follows your price changes, this is all you need to know. Analysis of its decision-making process would be redundant. Always be alert to reliable patterns of simple behavior. 5. Chance, the role of luck. Luck and chance are not necessarily accurate descriptions of unexpected results, but most markets, companies, and business units are complex systems that are sensitive to initial conditions. Therefore, expect the unexpected, and expect it often to be due to minute and undetectable causes. There are several corollaries. Don't expect to be able to control everything. Don't be thrown totally off course when the unexpected happens. Build flexibility into your plans. If X happens, do Y. If W happens, do Z. When something goes wrong, don't waste enormous effort investigating what went wrong and punishing the wrongdoers. Annoyingly, there may be no wrongdoers, or the wrongdoers may have behaved impeccably as per your instructions. Get on with working out what to do next. And finally, when something goes right, remember that it may not be at all due to your skill or that of your firm. It may be sensitive dependence on initial conditions that happen to suit you brilliantly. Exploit the trend for all it is worth, but don't believe your own propaganda. The next sensitive dependence may suit a competitor better. 6. Chance, the need for multiple strategies. Where there is major uncertainty about how an industry may evolve, it may make sense to have more than a single strategy. Eric D. Beinhocker comments that in 1988, when he wandered around Comdex, the computer industry's trade show, there was something very odd and ambivalent about the Microsoft booth. He wrote, "While most booths focused on a single blockbuster technology, Microsoft's resembled a Middle Eastern bazaar. In one corner, the company was previewing the second version of Windows. In another, it touted its latest release of DOS. Elsewhere, it was displaying OS 2 and major new releases of Word, Excel, and SCO Unix. What am I supposed to make of all this?" grumbled a corporate buyer standing next to me. Columnists wrote that Microsoft was adrift and had no strategy. Reporters told stories of infighting at the company, as one group worked furiously on Windows and DOS, while others poured their energies into OS 2, Mac applications, and Unix. In 1988, it wasn't obvious which operating system would win. In the face of this uncertainty, Microsoft followed the only robust strategy, betting on every horse to win. Microsoft had strategies rather than a strategy. Focus is a wonderful thing, but corporations in fast-moving and unpredictable markets may need to take some of their resources and have a few side bets at long odds. This is equivalent to spending money on financial call options. As Beinhocker comments, a company should use most of its resources to build its current activities, but the resources devoted to riskier experiments further afield are critically important, since they could contain the seeds of success in a currently unimaginable future. 7. The first mover advantage. Since most complex systems are very sensitive to initial conditions, it makes sense to get in on the ground floor of any new development that may be important to your key markets. The idea of the first mover advantage, that the first person in has an edge over other equally qualified latecomers, is well known in business, but the science of chaos reinforces its importance. A firm that, in an embryonic market, puts out a product that is, say, 10% more attractive than any other offering may end up with a 100 or 200% greater market share, even if competitors later provide something better. The first mover advantage locks in standards and makes the market behave in ways that are tilted to favor the first mover. A cute illustration of this from chaos theorists is the way that clocks behave. Why should nearly all clocks exhibit 12 hours and move to the right, that is, clockwise? This is not inevitable. Why not a 24-hour face and have the clock hands move to the left? If you think this is silly, go to Florence Cathedral and observe its clock move counterclockwise through 24 hours. The cathedral and the clock date from 1442. At that time, the convention was open. Shortly after, clockmakers standardized on our 12-hour clockwise convention. Yet, if 51% of clocks had ever been like the one in Florence, we would now be reading a 24-hour clock backwards, and the clock in the first line of George Orwell's 1984 would not have shocked readers by chiming 13. The early bird captures the convention, and hence the competitive advantage. So get to market, quickly, establish the standard, and grab competitive advantage while the field is still fallow. And finally, 8. Business is fractal. There is too much uncertainty and uniqueness in business. In the language of chaos, business is too fractal and too sensitive to initial conditions to allow for paint-by-number strategies, to slavishly follow well-worn rules of thumb. This does not mean that we should give up and make most decisions by tossing a die. A large part of the difference between successful and unsuccessful executives and entrepreneurs is the ability to recognize fractal patterns and make decisions accordingly. If you spend your lifetime looking at clouds or coastlines, you will make a better guess than most people at whether it is going to rain or which way the coast will run beyond the point you can see. If you have many years' experience and track record at making good decisions in a particular industry and market, the odds are that you will continue to make good decisions by recognizing recurrent patterns, as long as you stay in the same industry and market. One of the sad things about modern corporate life is how often operating managers, who know their markets well, are overruled simply because they are unable to explain or rationalize their instincts to their corporate bosses. A more sensible setup would not require explanations. It would just judge by results. Recognizing that business is fractal gives you many very important warning and encouraging signals. Here are some of them. 1. Experience and intuition will usually win over analysis because the analysis can never be precise enough or conclusive. Analysis is, of course, useful as a supplement to intuition. And as we have seen earlier, the intuition-analysis dichotomy is in some ways a false one. Good intuition is the crystallization of previous analyses, and good analysis is often the exploration of intuitive hypotheses by collecting data. Yet, so great is the importance of recognizing fractal patterns and what previously went along with them by way of results, realizing that the position now is more similar to previous situation A than it is to previous situation B, and that situation A led to disaster, for example, that someone who is a great manager and analyst may well lose out to an apparently lazy but cunning old hand. 2. At the very least, recognize that business is fractal and that slight differences in inputs can lead to totally different outcomes, should teach us to be humble when we enter adjacent new markets. These may look the same as the old markets, and yet be subtly different, with shocking results. If you doubt this, look at the terrible track record of most retailers the first time they venture beyond their home country. Part of the problem is that head office tends to export its own proven formula, proven that is in a different market, and brushes aside the objections or alternative models proffered by local managers. The local people can't produce analyses to validate their hunches. Head office, apparently reasonably, insists, "Do it our way until you can demonstrate the logic of yours." Then the foreign approach fails. No one can say why. The missing explanation is simply that business is fractal. 3. Whenever you face an important decision, try to find the nearest equivalent situation in your experience, or that of colleagues or friends. Do not leap to conclusions. Engage in sober debate about the possibilities. Unless you are very certain, draw up a top 3 list of possible similar situations and what happened next. And finally, 4. Once you have headed down a particular path, be aware that you may have made the wrong decision. Look for the early signs that you are on or off the expected path, just as you would when following a map. If the early signs are not what you expect, you have probably chosen the wrong fractal comparison. Because there are so many different types of business, where different rules apply, specialized businesses always have an advantage over generalized ones. A specialized unit, company, or market will generally win over an undifferentiated one. Where possible, therefore, form specialized teams, new business units, new divisions, and above all, new companies. Business is generally reluctant to follow these steps, and increasingly reluctant as the order I have given ascends. A specialized team? Maybe. Splitting the company in 2? No way. Yet if business is fractal, and part of the skill in business is recognizing fractal patterns, a specialized company will be much better placed to recognize the right patterns and make the right responses. A specialized team will go some way toward this benefit, but be constrained by the degree to which it shares resources or decision-making with other parts of the organization that deal with different sorts of patterns. Complexity and emergence. Most of the radical scientific innovators that gave us chaos have now moved on to the more topical study of complexity. Complexity is the study of complex systems that manage to produce their own brand of order. Sometimes this hints at deep simplicity behind the complexity, especially when the same simple yet baffling patterns emerge in completely different types of complex systems. An economic slump, it transpires, is very much like a hurricane, with similar feedback causes and effects. A developing city is very like a growing embryo. Complexity builds on the insights from chaos, but adds 3 new themes. First, complexity focuses on complicated feedback systems and shows that these usually have surprising results. Second, as Philip Anderson, widely regarded as the founder of complexity, urged, complexity is about emergence, how groups or wholes, that's WHOLES, behave quite differently from the aggregation of their individual characteristics. In combining individual units, individual customers, water molecules, body cells, business units, single birds, whatever, into groups, into markets, steam, a butterfly wing, a company, a flock, we may emerge with something completely unexpected and different from what we started with. Third, what complexity is really interested in is self-organizing systems. That is, systems that start in a similar or random state, but somehow organize themselves, quite spontaneously, into a large-scale pattern. Self-organizing systems. Spontaneous self-organization is a fascinating thing, especially when the individual components are so numerous and apparently unrelated to each other. Adam Smith, although he didn't know it, was an early exponent of complexity, talking about the invisible hand that seemed to direct the self-interested intentions of millions of producers to satisfy the self-interest of millions of consumers. Think of the billions of interconnected neurons in your brain, producing a result that surely an individual neuron could not envisage, and yet organizing effectively to ensure that you can understand my words. Think of a way that a city that starts out by being racially integrated soon divides itself into racial or social or lifestyle groups. Self-organization, incidentally, is not always a benign force. Think of the way that a stock market crash, or a hurricane, or an earthquake, or a meteorite organizes itself from its constituent parts. Think of how atoms combine into molecules by forming chemical bonds with each other. The molecules are quite different from, and more complex than, the atoms whence they came. Or think of the Internet. Nobody planned its evolution from being a research tool of government and universities into what it is today, a global network giving information and power to consumers that will trigger the biggest and fastest change in industry and corporate structures ever seen. The Internet has a life of its own and decides what it will become as it goes along. Complex systems are adaptive. Self-organizing systems that are complex are also adaptive. They adapt to their surroundings and try to turn what is happening to their advantage. The brain develops and learns. Species evolve. Cities respond to new inputs. Markets become larger and more specialized and adapt to pressure from important distant markets. Complexity is linked to evolution by natural selection. For example, a termite colony adjusts the number of its different castes by cascades of chemicals activated in the termite larvae. If there are too few soldier termites, the smell given off by them in the colony falls below a certain level. And then the larvae nursery automatically produces more soldier termites, which differ physically from other termites. John Tyler Bonner has shown this type of self-adjusting complexity evolves by natural selection. If this happens in nature, is it fanciful to see the emergence of complex systems, such as cities and economies, as part of the same process of evolution by natural selection? Complexity theorists such as John Holland explain that complex adaptive systems typically have many niches, each with a specialized role and place. The new niches are always unfolding. Niches for new predators, for new prey, for new symbiotic partners, for new parasites. As new niches open up, the system changes. It can never be in equilibrium.